Thank you. It's a pleasure to be here and very nice to see you all here. So I just learned that you actually went through some substantial classes during these last 3 years. So this will also be opportunity for me to ask you some questions and see what you already know about this. I think this is going to be a very gentle introductory story to remind you about some topics. I'm going to talk about principles of instruments, like for example, telescopes, spectrographs, filters, and so on. But I will also talk to you about the physics of these objects and how the physics connects to what we observe here. So my specialty is analysis of spectra of the sun. And basically what I try to do in my science life, I try to devise methods that connect what we see and what is the spectral distribution of the light that comes from the sun to us with the physics that happens in the atmosphere of the sun. So obviously the most examples will be from my field because I'm the most comfortable that way, but always keep in mind that these things apply for most of the astrophysical objects. And out of these three, let's say, observational disciplines, we will of course dedicate the most attention to spectroscopy. First, because I think I know it the best of all of these three things here, and also because spectroscopy marked the birth of what we today call astrophysics. So astronomy is a very old, very ancient science that exists already for multiple thousands of years, as you probably know. But astrophysics, what we call astrophysics now, is very young. It's maybe 200 years old or something like that. So we will also go a little bit through that history and remind you of some of these concepts there. So let's start with a picture that is very non-local. You know, initially the topic of this lecture was supposed to be spectroscopy, photometry, and astrometry of nearby objects. These are not nearby objects. These are galaxies. And this is maybe the most famous astrophysical image ever made. This is so-called Hubble Ultra Deep Field. And you have probably seen this somewhere. And obligatory reminder that these colors are fake, but they probably do represent a little bit how these objects would look for real. When we observe, we do not see color. We need to infer color, basically, through the measurement, because we don't use our eyes anymore. We use cameras and chips and things like that. So tell me one thing. What can we learn from this image on its own? Is there something that we could do scientifically with this image to learn something?
Well, we can count galaxies.
We can count galaxies, exactly.
How much of them is in space?
Exactly. How much of them is in various parts of space? If we had this image, this is very small part of the sky, but if we had bigger part of the sky, we could see on which spatial scales are distributed, calculate something called power spectrum. We could maybe let this go through a spectrograph and then look at the red shifts of these galaxies, try to infer how fast they move. We could try to somehow infer from the apparent light of these galaxies and the expected light how far away they are, and so on and so on, right? Or how bright they are, etc. Obviously, I couldn't go for 1 minute without doing something extra to this image, right? Just by looking at the image, you can't really do much except do statistics or counting or something like that. If you really want to look at the physics, you need to look at the spectra. However, the reason why I brought up this image is because I have to ask you some questions about telescopes before we go on. So this image was made by Hubble Space Telescope, maybe the most famous telescope until now. It used to be our biggest telescope in space. It's not anymore. Now it's James Webb Space Telescope. But still, for a telescope that was launched in 1990s, it was absolutely huge. So it had a 2.4 meter, it still has actually 2.4 meter wide, actually it's more than this, right? Wide primary mirror. It has focal length of 57.6 meters. And it already works for more than 30 years. So it's a fantastic thing, right? Now a question comes for you. Why does the size of this mirror matter? Why does the focal length of the telescope matter? And since we were talking about an image here, what is an image? Let's start from the last one. What is for you, astronomically speaking, an image? How would you define an image to somebody? It's the light that we get. Can we be a little bit more specific? It consists of the light we get, yes. On the specific wavelength, very good.
Information about brightness of each pixel.
So very good. I like that one a lot. It's information about the brightness of each pixel in the detector that we are using to record something, right? So basically, image is the distribution of the brightness in some plane that corresponds to a specific solid angle in the sky, right? So now I'm looking at you, and my solid angle is some, I don't know, 60 times 60 degrees, okay? And what I see, the image of you in my eye is basically the distribution of the brightness, but now I'm also sensitive to color, which we typically are not when we use CCD. So I also see like which colors are your shirts or your hair or your eyes and so on and so on. So that's an image. An image is something that we want to record. So we will try to remember now by talking about the telescopes, how do we record these images? But let's then also answer these two questions. Why does the size of the primary lens, I called it lens here, even though for Hubble it's a mirror. Why does the diameter of primary aperture, let's call it aperture, why does it matter? Why do we want wide telescopes? What do we achieve that way?
Well, we just connect with a larger space for light.
Collect more light, excellent.
And that's why we can see objects that are really far away. And
It's really far away, excellent.
so, and like that's it.
I think there is one more reason. So one reason is that we want to collect more light with the bigger telescope. That makes complete sense, right? This is also why our pupils open up in the night, because we want to collect more light, right? We want big telescopes collect a lot of light, we can see fainter objects, less bright objects. But there is one more reason why we are building bigger telescopes. Can anybody think of it?
With a big telescope we can detect little objects.
Little in which way? Yes. Very good.
Little in the sky.
Yeah? What is the property that is related to that? Okay, let's ask a question this way. What is resolution for you? When I say such and such resolution. If we are gamers, like I am, for example, when I think about resolution, I think about how much pixels I have in my screen. But I'm also an astronomer, so now I'm already trained to, when I think of resolution, to think of something else. And that is?
Well, resolution is the smallest angle that we can like detect between two objects.
Exactly. So basically, the bigger the telescope is, the smaller distances or maybe smaller angular separations in the sky we can separate, which is one way to say that we can see very small details in the objects, right? And that's not really intuitive, but when you go through all the calculations of the diffraction and so on, that we probably don't have time to go through that, but we will mention it again here, you will actually see that the bigger your mirror is, or your lens is, the clearer, the more crisp your image is, which is one of the reasons, especially when we want to look at the objects of finite size. What are the objects of finite size? Sun, nebula, galaxies, planets, things in the solar system, everything that is not a point, but we actually can resolve the image, then is when our resolution of our instrument really comes into play, because we want to see small details there. And that is another reason why we make really, really big telescopes. Okay, very good. What about the focal length? What does focal length of a telescope do? You can relate it, if somebody is into, photography, you can relate it to what you know from photography.
Well, maybe focal length determine the size of an image on the matrix.
Exactly. I will have to forbid you from answering some questions for a little bit, but we'll get back, don't worry. Yeah, exactly. We will get back to that later. I will show you on a scheme, but basically having telescopes with big focal length allows us to stretch the images over bigger area, which means that we can, we basically get better what we would call zoom, right? But keep in mind that our, again, zoom doesn't really work the way that we are imagining it, right? The zoom only depends on how basically big part of the sky you cover with your little chip there. I have some schemes later that will outline this better, so let's keep going there. Once again, this image here was basically created by using this huge telescope. So telescope was to begin with, it was able to collect a lot of light. It has huge focal length. So this is actually a very small part of the sky stretched out on the chip of the Hubble Space Telescope. And because it was in space, it still is in space. Because it is in space, it has two huge benefits. One benefit is that there is no Earth's atmosphere to ruin the image. You probably know that's the reason why we launch the telescopes outside. The other reason is it's always night for it, right? It is simply faced away from the sun, so it could expose for very, very long time, pointing at this part of the sky here. So it could really accumulate a lot of photons, and here we can in principle see some very, very faint objects. So that's another way for us to see very faint objects, not only to have huge telescope, but to have huge exposures. I will tell you later when we talk a little bit more about some closer objects, like for example sun or the asteroids or other objects in the solar system that we can't really expose for too long, because we actually see these objects evolving in front of our eyes. Not really evolving in the sense that stars evolve, but we see them changing, so we cannot use huge exposures there. Okay, very good. And this is something that you know, right? That basically the principle on which telescopes work is just to have some sort of collecting element. Collecting, well, maybe a better way to say it is that we have some element, this is here a lens, that reshapes the shape of the wavefront. What is the wavefront? Where wavefront is the plane that is perpendicular to the direction of propagation of the waves. And we have a star which is very, very far away. So for example, over there on a different hill, the light that comes from that star, basically the rays, even though the rays don't really exist, what really exists is the oscillation of the electric and magnetic field. But these rays are basically parallel, right? The way how we would model the light of that star coming to us would be like something called plane monochromatic. Well, it doesn't have to be monochromatic, but simply a plane wave, right? It's just some constant times e to the I kx minus omega t or something like that, right? And then that plane wave arrives to our lens or our mirror, and the shape of the wavefront changes, and this lens collects all the light here in one point. And this point here is what we would call an image of this specific star, right? Okay, now a question for you, which is apparently very simple, and you maybe already know the answer, but tell me just in case. If we now had another plane wave coming from a different direction, let's say from here, would it be focused in the same point or in a different point? Who thinks different? Who thinks same? Nobody. You're right, it's a different point. Right, so if we had a different star emitting, for example, lying somewhere down there where that factory is, coming under a slightly different angle, it would be focused somewhere here, right? It's a very deceiving thing. Sometimes people think that the lenses just focus all the light in the same point. If that was true, we could never see anything, because our eyes would just focus all the light in one point, and then we could not distinguish what is left, what is right, what is up, what is down, right? So that's the principle, that the plane waves coming from different directions get focused at different points in this so-called focal plane. We put our detector there, we record how much light arrives, and we get an image. And that's it, right? And basically the simplest telescope, and we still try to make telescopes like this today, to really have as few mirrors and lenses as possible. The simplest telescope would be just one lens or mirror and then a camera put in the so-called primary focus, right? The thing is that due to practical reasons, we very often want to reshape the path of the light. So we will very often have multiple, foci, multiple focuses, and then our telescope will contain more than one lens or mirror. And in the process, we can, for example, achieve that we have huge focal length in a small package, or we can, reshape our wavefront in a different ways, and we will also lose some light and spoil our image a little bit further on the way, but that's how it goes. Oh, here they are, in case I need. Okay, very good. What do we have next here? Well, this is something very simple that you already know. This is how image is formed. I have an object here, which I model as a lot of points. Each of these points is a sort of source of harmonic plane waves. They get to the lens. They get focused. I'm not drawing all these individual rays here. I'm just drawing the object and the image. For us, this distance from the lens to the object is very far away. So we basically, whenever we do astronomy, we assume that the object is formed in the focus, right? Because all the objects that we observe are infinitely far away. When we do photography, it's not really like that, right? Sometimes objects are a little bit close, so we need to focus a little bit. We need to change the position of our chip with respect to the lens in order to really have our object in focus. Very good. Cool. Well, but that's not the end of the story. If it was like this, it would be beautiful. We would use our lenses, we would get very nice images, very sharp images. We would just make bigger and bigger telescopes to collect more and more light, and that would be the end of the story. But there is more to this story, and you're maybe familiar with this thing here. And that is that this harmonic plane wave, when it arrives to the opening of the telescope, and this opening can be the primary opening in case when you have a mirror, or it can just be the opening where you put your lens if you have a refracting telescope. What will happen of this opening is that we will have some diffraction. Now, what is a diffraction? There are many various ways to describe it, and people call it the bending of the light or blah or blah. I just like to say that diffraction is the natural consequence of light encountering an obstacle. When that happens, the obstacle behaves as a secondary source of harmonic plane waves, and because that obstacle has finite size, it's not infinitely big, then these waves will interfere. And as a consequence of that interference, what we will get is that the light that previously propagated only along one direction will now get redistributed in directions. And instead of having just one dot here on the screen, what we will have is we will have a smudge, like a circle, and then these rings around. And this central part here is called airy disk, and these rings are called, well, I don't know, I just call them rings. And the equation that describes this is this equation here. This is the equation for the diffraction on the circular aperture. This here is Bessel function of the first kind of the order 1. This u is a derived quantity, which basically depends on the size of our opening, on the wave number of our light, which is 2 pi over lambda, and on the angle theta. What is the angle theta? It's the angle that measures the direction of the outgoing ray with respect to the central, right? And if there was no diffraction, somehow magically, then this equation would turn into a delta function. You know what delta function is, right? It's something that is basically infinity in only one direction and 0 everywhere else. Here, because we have a finite opening, what we get is we get the spreading of our light in this shape. And paradoxically, and I'm again sure that you know of all this, but again, take a moment to remind yourself of this one. The bigger the opening here is, the smaller this point here is, right? The more I open my light, my telescope to the bigger telescope I have, the less of this diffraction I have here, right? How can you always remember that and not get confused? Well, if this was just a point source, if it was infinitely small, then the diffracted light would basically go equally into all directions because this would behave as a point source, so you would have maximum diffraction. If it was infinitely big, it means that there is no opening at all and the light just continues the way it was and it just propagates along one direction. And don't be confused. One confusing thing here is typically that you are like, well, okay, there is this circle here and this circle here is this thing here. No, it's not how it works. Like in typical experiments that we can set up here, this hole is very, very small. This circle here is very, very big. For telescope, we see this because telescope is supposed to focus this huge beam into one point, but instead of focusing it into one point, it focuses it in this thing here. So imagine that there is some, lens here that is now trying also to do focusing. And this is where this famous expression of some critical angle, which is equal to 1.22 times lambda over d come from. This critical angle here is the first zero of this equation here, and it determines something called resolving power, or the angular resolution of your telescope. And the better angular resolution you have, the smaller that angle over there is, the smaller details you can resolve in your image, right? And for example, with our eyes, we have some fundamental limit. Our eyes don't have infinite spatial resolution. So when I look, for example, at somebody sitting very high, I cannot see their, individual hairs. But when I look at somebody sitting very close, I can see their individual hairs, right? If I use the bigger instrument, I could maybe resolve it over there. We will see later how we use this principle to observe the sun. Cool. Yeah, this is what we already talked about. The bigger telescope we have, the smaller airy disk patterns we have, and we want as small patterns as possible. Of course, the story is not this simple. What actually happens in the real life is that you have a telescope, at least when it's on Earth, and that wavefront is further disturbed by the Earth's atmosphere. How can you model that? You can model that by saying that the wavefront, instead of being a nice plain parallel wave, it gets into the atmosphere. And it gets a little bit distorted. Because the air is somewhere more dense, somewhere more diluted. So the propagation of the wave has different speeds at different points, and our wavefront is no longer flat, it's distorted, which means that when I put my telescope here, my lens, different parts of the lens see my wave coming at different phases. And the great exercise for you, if you're interested in trying that, you can talk to me later, is to try to model this as assuming the aperture of your telescope to be complex. So aperture of your telescope does not anymore just decide where the light passes through and where it doesn't. It also determines what's the phase of the light that passes through, which is a very neat trick, and we can talk more about that later. Also, another complication is that, let me see if that comes now. Yeah, it comes, is that the openings of the telescopes are never perfect circles. They are often, especially for the space telescopes, because space telescopes tend to be, we try to make them compact, which means that there is never free opening, in the telescope. There is always some sort of obstruction because we, for example, want to put a secondary mirror, like in the case of Hubble, or in the case of James Webb Space Telescope, we want a secondary mirror, and our mirror is segmented to begin with. So the diffraction pattern of such opening or such opening is much more complicated. Does anybody know how would you find the diffraction pattern of something that is not describable by a function, right? So circle is very simple, but this is not circle. How would you find diffraction pattern of this? Do you maybe know?
By experiment.
By experiment, very good, but actually that's the best way, yeah. But for example, if I now gave you this image and told you, calculate this for me in my computer. Well, the most useful thing in physics is probably Fourier transform. And believe it or not, the diffraction pattern that we see coming out of our telescope is actually the Fourier transform of the opening. So this function here is the Fourier transform of circle. And these are the Fourier transforms of these openings here. So in case that you were wondering why, when we look at these fancy images of stars in the sky and they have these, beams here. These beams come from the very complicated shapes of the opening apertures. Right, very good. Okay, let's keep moving. So this leads us to this, very important equation that you probably used a lot of time in your life, which is called, and basically leads us to this thing called the Rayleigh criterion, where we say that if two objects are closer than this distance, we cannot resolve them. We think it's one object. If they are further away than this angular distance, then we see them separately. And this is, of course, very important. For example, if you want to resolve optical binary stars, if you want to see details in the sun, in the nebulae, in the galaxies, in anything like that, right? Even if you want to try to directly image an exoplanet or something like that. Yeah, there are two important consequences. One is that we have been talking about for a while now, that the larger primary mirror or lens is, the better the resolution we get. Basically, larger the primary aperture is. But there is another consequence, which is that larger the wavelength is, we have worse resolution. And that is reason why you will never get beautiful images with the radio telescope. We really have to use interferometry with huge radio telescopes, like they did when they observed this accretion around the black hole a few years ago. You probably remember that, in order to see very small details, right? And why we, for example, like to perform observations in UV, even though we have to launch telescope outside, because UV means small wavelength, means very good angular resolution. Very good. And this is basically how it works when we have the two sources now, and this is now from the optical size. I have two beams of, basically I have two plane parallel waves impinging on my lens, and they are making two images, and both of these images are smeared a little bit because of the diffraction, and that basically explains you this thing here, right? Now the question is, of course, what would happen if I had image, if I didn't have two separate sources, or 3 or 5 or 7, if I had a continuous, if I had basically what we call a finite source, like sun, like planet, like moon or something like that. In that case, what actually happens is that my ideal image that I would like to see gets blurred by the effect of the telescope. And the mathematical operation that you can use to depict that is that my image that I'm actually observing in my plane, in my focal plane, is my original image convolved with the shape of my so-called point spread function. What's a point spread function? Where it's this diffraction pattern of the telescope that we just talked about. I'm sure you are familiar with this, if not from astrophysics, then from some other source, right? And what we actually try to do today, especially in my field, is we try to undo this operation. So we know that our telescope is convolving our ideal image. We try to find this as well as we can, and it's especially easy, as you said, through experiments for telescopes that are in space, because you basically measure this once and you know it more or less forever, and then you can try to undo this operation, which is not as trivial as it sounds, because this is some double integral which contains some kernels there, and you need to invert that integral in a way. But what is especially hard is to undo this equation when we observe from the Earth, because then this function here changes as our atmosphere changes. And the whole large field called image restoration techniques was born that way by people trying to infer and to understand how to basically model or approximate this equation, this function here, as it changes very, very quickly through time. And one of the ways that we use to help ourselves that way is to make images with very, very short exposure times. And that's especially good when we, for example, observe the sun, because sun is very bright, so images coming from the sun already have a lot of photons, so we can use short exposures. I will show you later some results of this, and for example, in how much detail we can see the sun today. Very good. This is something that we already discussed. Somebody actually literally said what was on this plot here. This is just to tell you that basically the size of your focal length, which is the distance from your lens to your chip, assuming that you put chip in the focus, will basically determine the size of the image here. And here you have example of, this is the image of the sun in one of the telescopes with very, very big focal length. This is McMath infrared solar telescope in US. I think it has focal length of something like 80 meters. And this is huge image of the sun. This is like meter or 80 centimeters or something like that. So even though the telescope is huge, because the image is stretched over such a huge, surface, actually, I think you can even maybe put your hand here or something like that. You wouldn't get burned because the light is spread over a huge surface. Right. Of course, we want to use large focal lengths when we want to have big images, when we want to sample our images with a lot of pixels. But of course, it can be counterproductive in the case when our source is not bright enough, because in that case, we only get few photons per pixel, and we can get eaten by the noise, which is another thing that we're not going to be talking about today, but it's a very important thing in astrophysical observations. Right. So we kind of understand now how a very simple telescope works, right? We just need some collecting element, and we can supplement that with more lenses or mirrors if we want, but eventually we will get some focus. And in that focus, we will put our detector, which back in the day was, back in the day it worked in a different way, right? You have to put an eyepiece. An eyepiece would again provide you with basically plane wave, and then that plane wave would enter your eyes, and it would be as if you're looking, with your own eyes at something that is very far away, just re-imaged, basically zoomed in, if you want. But we don't need the eyepieces today because we just directly record these images. First, we use these photoplates, then we use the photo detectors, and now today we use CCDs and CMOS cameras, which are basically same things as we have in our phones. Right. Cool. And when we have an image, basically we can track where the objects are, track how they move. In the image, we can ascribe them some coordinates and so on and so on. And this field is called astrometry. And basically, astronomy was astrometry for thousands of years. People were always looking where the things are in the sky. They were trying to represent that with some coordinates. Eventually, they were able to make more and more precise observations. Then back in 15th, 16th century, there was Kepler, Newton, all these people who had really precise measurements. They allowed them to build the theory of gravity, to test the theory of gravity. Then it allowed the people who succeeded them, like Laplace, Gauss, and so on, to create more sophisticated theories by now perturbing these basic gravitational equations by allowing for interaction between multiple bodies, and then they were able to observe these because they had even more precise observations, and so on and so on. Right. And that is literally only based on tracking where the objects move. And from movement of the objects, we can learn something about the dynamics. The dynamics meaning how they move, what are their accelerations, what are the forces between these objects here. And one of the maybe most impressive and interesting results of such an observation is you can observe the stars that are moving around what we now know is a black hole in the center of our galaxy. So what people were doing, they said, well, okay, if there is a black hole in the center of our galaxy, then we won't be able, obviously, to see it directly, right? This is just a, artist depiction. This is not really how it looks like. This is how it looks like, right? So what we can do is we can observe the stars that are very close to that object, whatever it is, and we can very precisely measure their coordinates and see how their coordinates change with time. And when you do something like that and put this data on a graph, you get something like this. You get that from one star, measuring its position for 10 years. So look at here. It starts in 1992. The last observation is in 2002. You measure periodically its position. Its position traverses some sort of ellipse, right? Then you can fit this ellipse. You can find the parameters of this ellipse. You can find what its major semi-axis is and the period of this star, right? Because from this we can infer, I think, that the period is something probably like 14, 15 years. From these two quantities, You can find out very simply, you probably did it many times, solving the problems in astrophysics, you can find very easily what is the mass of the object responsible for such a motion. And when you do that, you get that it's millions of solar masses. You get an object which is millions of solar masses, you don't see it anywhere in the sky. Well, obviously that has to be a black hole. So this is the first direct confirmation that there is a black hole in the center of our galaxy. And we found it by pure astrometry, just tracking how star or stars are moving. And this is a very simple exercise that you can do. You can find this data online, you can plot it using Python or something, you will get these points there. Then you need to use some tricks to figure out how to fit that. You will get the parameters of this ellipse. Maybe you already did that? Something similar throughout your exercises and labs? No? Yes? Well, okay, give it a thought, consider it. I can show you how to do that. And you can measure this. Yeah. The thing is that we don't have to use it only for black holes. We can use it also for just regular binary stars. So from a long time ago, people figured out, for example, looking at Sirius A and Sirius B, or here looking for, two stars in the Alpha Centauri, which is actually 2 stars, or maybe even more than 2. You can see when you do very precise measurements that these stars change their position. And then by basically plotting the coordinates of one with respect to the coordinates of other, you always get some sort of an ellipse. From that ellipse and its shape and the period, you can get the dynamical parameters of the system. You can figure out what are their masses, how is the orbit oriented toward you, and so on and so on. Then you can do that for many, many, many pairs of these binary stars, and you will get, you can get some statistics, you can figure out how are these systems oriented, and that teaches you something about the stellar populations. Okay. But one thing that we cannot learn by just measuring the positions is we don't know the temperatures of these stars, we don't know their sizes, we don't know their chemical composition, and so on and so on. These are the things that we cannot know until we do something more to this light. And that more that we're going to do is we're going to put it through a spectrometer, right? And figure out what's the wavelength composition of the light that comes through this. But we have to wait a little bit, because before that, we have to do something called photometry. So one thing, we were now just talking about what is the position of the star or any object in the sky. I mean, there are many more examples of astrometry. You all know that, for example, Uranus and Neptune and Pluto, I guess, also were basically found by just tracking the motion of the other planets in the solar system and seeing that these, orbits are a little bit perturbed, and then people calculated where and what kind of object it is that causes such a perturbation, and they just took the telescope, pointed it there, and yeah, the planet was there, right? However, so far we didn't take into account that we can also measure how bright the object is. And measuring how bright something is called photometry. And typically, we would distinguish between so-called absolute, this should be B. In Serbian, we would call absolute photometry. Absolute photometry, which is you somehow try to calibrate your instrument to directly measure how bright something is in physical units. But what we actually do most of the time is we do the so-called relative photometry, which means that whenever we observe something, a star, an asteroid, whatever, we try to make sure that in the same field of view there is an object of known brightness, and then we can compare their brightnesses and find the brightness of our unknown object, and then we can track it through time and do our science with it. And I think you all know what magnitudes are and how the magnitudes relate to these quantities. Basically, the physical quantity that we measure on the Earth is something called irradiance. I typically denote it with epsilon, right? It's basically received energy. Let's actually use these per unit surface. I'll use A per unit time, right? So units for this are watts per meter squared, right? Or we could say spectral irradiance would be the energy, the received, again, energy per unit surface, unit time, unit wavelength, right? And here it would be watts per meter squared. And just to emphasize that it's the wavelength, so this is not correct way to do it, but I'm going to put angstrom here. Because if I put meter to the cube, it becomes confusing, right? It's like, what is meter to the, why watts per meter to the cube? This way you know that this corresponds to surface, this corresponds to wavelength here, right? And then we can define magnitudes, right? We can say that M1 minus some referent, M0 is 2.5 log epsilon 0 over epsilon 1. So if this is some reference star and this is some reference star, you can relate these two quantities. Right, this is just a different way of expressing irradiances through magnitudes. Right. What actually is more interesting for us is to say, let's say that we measure the brightness of something, like a star or a star-planet system or an asteroid or something like that. What can we learn from that? What can we learn from that? I didn't ask you anything for a while. Let's say I'm looking at the star. Star is changing its brightness. Why? Mm-hmm. Let's go deeper. Why would it be variable star? What makes stars variable?
The second star, the exoplanet, the
Amazing.
black hole around the star.
Okay, black hole around the star, maybe a little bit exotic, but sure, can be. Yeah, exactly. So star can be variable on its own. For example, pulsating stars. I forgot to put them in the presentation, but keep in mind that they also exist. Like stars can physically change. There can be physical processes in the stellar envelopes that make them pulsate, that make them change their brightness in time. But there are more things. Like, for example, one thing is that you have these so-called closed binary systems. Closed meaning that the stars that are in the system are very, very close to each other. Sometimes they are so close to each other that their shapes distort. So you have two stars that are so close to each other that gravity is such that they are not spheres anymore. They have this egg shape here. And now this system, of course, is not fixed. It's rotating. They're rotating over each other in this weird shape. And then as you're looking at them, as the time passes, you see different and different projection, and obviously in this projection here, you're going to see more light than if one star is in front of the other. But because they are so close and their shapes are so weird, you get the variation of the light that is very irregular, right? You get the so-called light curve that is complicated. That is not trivial. Like this here is a simple light curve. I have two separate stars. They're almost spheres. This is what we would call detached system, right? And when the brighter star is in front of the less bright, let's assume that this one is brighter, this one less bright, doesn't have to be. When the brighter star is in front of the less bright, we have the secondary minimum. When the less bright is in front of the brighter, we have the primary minimum. And this is what you know, right? This is what transits are. We're going to see in a little bit the transit of an exoplanet as well. But here the situation is much more complicated because these stars are not really detached anymore, right? They are what we would call here semi-detached. So they are so close to each other, their envelopes blew up through the stellar evolution so much that their shapes now are irregular, and we get things like this. What you can get eventually is so-called contact binary systems, where one star inflated so much, for example, through evolution to the red giant phase, that the matter started flowing through this contact point here, which is one of these famous Lagrange points, from one member of the binary star system to the other one. And you literally have what we call the Roche lobe overflow, where you have the stars that are now one object, technically speaking. And now you can see that actually ways to interpret these light curves are very similar what people use in computer graphics, right? You somehow need to model these 3D objects. You need to understand how their brightness changed from one point to the other. Why would it change from one point to the other? Because now we also have this weird situation because our star is not of the regular shape. Its temperature is different as different parts on the surface. Then they can have the so-called star spots, which means that some parts of the star can be brighter or less bright than the remainder, right? So you can take all these things into account. You can solve a problem of basically synthesizing this so-called light curve. And then you do that many, many times to find the combination of the physical parameters that corresponds to what you see here. And this procedure is called so-called light curve fitting. And through that process, you get same things as we could get before for the visual binary stars. We can get their masses, their periods, and so on. But we also get the distribution of the temperatures on their surface. We can infer the presence of the bright spots or the dark spots, and so on, and so on. And this is actually, maybe this field is past its prime, but it's still very, very interesting. It is still important to interpret these because the binary, first of all, a lot of stars are in binary systems. And the other thing is that binary systems are some kind of natural laboratories for the stellar evolution, because we can, analyze what happens there and then compare with individual stars. And we can learn a lot from these light curves that tells us something about the physics of these involved stars. By the way, one thing that you should always keep in mind is that astrophysics is before, I'm a theorist, but still, astrophysics is before everything observational science. Like everything that we model, everything that we calculate, everything that we predict, we want to detect it, right? Nobody ever got a Nobel Prize for anything that was unconfirmed, right? People waited 40 years to convert Higgs boson to, for inflation and all these things. Right. So what we do here is we have this disadvantage compared, for example, with experimental physics, that we can't really do experiments. We have to look for experiments that nature gives us. So that's why, for example, binary stars are very important, because there we get a lot of information that we couldn't otherwise. This is why sun is very important, because sun is very close. We see it in a lot of detail. By learning about processes that happen on the sun, we learn something fundamental about astrophysical plasma, and we apply it to other stars or even other objects in the universe. Okay, good. This is a very similar thing, but a miniature version. We can also look at these light curves when we observe the planets, right? Of course, we don't observe planets directly, we look at the stars, and sometimes it happens that the brightness of the stars very, very briefly dips like this, right? Then you look and you see how this dip looks like when you zoom, and it looks like this. So here you can see that flux only changes by 0.6% during this dip here. Compare it to here, where you had like a change of 60%, and this tells you that the object that occults the star here has to be much, 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 much smaller. So already by the size of this dip here, you can infer how big the object is, and typically it turns out that it's planet-sized, right? And these observations are made with one of the most important space missions ever to be launched. You probably heard of it. It's called Kepler, or it was called Kepler. I don't think it works anymore. Soon we will launch a successor of Kepler. It's called Plato. And Kepler did very precise photometry in a moderately sized field of view, and it basically scanned through this field of view, periodically observing stars and looking for the changes in the stellar brightness like this. And because Kepler was in space and very well made, it could make very, very accurate measurements, much more accurate than you could do, for example, from the Earth. And then you can see some very fancy things there. Like, for example, I want to ask you the following thing. When you take this light curve and you zoom even more, you actually see that this line here that looks straight with a very small dip actually is not straight. It goes up, 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 and then it dips down, and then it goes down, 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 and then here we have this huge occultation of the star, and here we have this huge occultation of the star. What happens here? I will wipe the board, because we'll need to draw this. Does anybody knows what happens here? Is this some sort of magic? Is this some sort of instrumental error, or is this real? Any ideas? Go, you're allowed.
It's because of the reflection of the light, and the planet reflects the light. So when it's like almost behind the star, it reflects all the light from the star with its surface. But after that, it's behind the star, so we can't see it, and that's when the flux goes down. Yeah, and that's it.
Perfect, perfect. So, what we are actually seeing is we do not see star and the planet separate. Like, this is our indirect way of inferring that the planet exists, right? So, what I'm drawing now is what we indirectly concluded that happens, which is exactly what our colleague just told us. When we have this primary occultation here, now I'm going to draw things in a different way. This is the star. We are looking from here, right? The occultation happens as the, okay, I'll draw the planet a little bit further away, like here. This is the planet, and as the planet passes through here, this is when I will have the first dip, the big dip, okay? Cool. Now the planet is here, right? Now what happens is that I see the full star, but planet also does something more than just occults the star. What it does is it reflects some of the light, right? But in this case, the light reflected is gonna go there, right? So this is like equivalent to, how do you call that? No moon, basically. In Serbia we call it young moon. I forgot the exact English expression. Like there is no light reflected toward us from the planet. New moon, yeah, exactly. But now, let's say that planet arrives here. Oh, nice. Now this part is illuminated and I'm seeing this part here, right? So now I see the star plus this small chunk here, right? As it goes more and more, just as it's about to set behind the star, I basically see this whole thing. So I see even more light than here, and then it dips behind, and I don't see anything. And that's exactly this thing here, right? You have the light that increases more and more as I'm seeing more and more of the reflected light from the planet, and then I see a dip here. So in a way, what we see here above this red line is the light of the planet itself. So in principle, if you could make measurements precise enough, and if you could somehow separate it, you could look how the light that is reflected from the planet looks like spectrally and so on and so on. You could analyze it, you could learn something about that planet. And that's why there is huge hype. The exoplanets are very popular because at some point, maybe in 20 years, maybe in 50 years, maybe in 500 years, we will be able to really look at the planetary light and very easily say, okay, there is methane there, there is oxygen, there is blah, blah, and so on and so on. Eventually, at some point, hopefully, we will discover life, which will, maybe be the greatest scientific discovery ever to be made. But about that, maybe on some other occasion. This is a fantastic thing, and I think that until we got Kepler, we couldn't see these very fine details in the light curves. All right. Here, just to sum it up, I'm jumping a little bit ahead and I'm presenting you some other exoplanet detection and characterization methods that you maybe already know of or you heard about that we won't talk about that much. So first of all, we have so precise measurements today, for example, with Gaia space mission, that we can see how the planet disturbs the position of the star on sky directly and detect exoplanets through astrometry that way. So this is like complete opposite of this thing with the black hole that I was telling you before. We can do this photometry that I just described right now. Sometimes the planets are so big and so far away from their stars that we can directly image them. And for that, we are trying to develop something called stellar coronagraphs, basically to obscure the stellar disk. We can do microlensing. Microlensing is basically the distortion of the light of the star due to the presence of the gravitational effects. And one of the most popular and maybe more important methods is to analyze how the Radial velocity of the star changes because of the presence of the planet. The way that we see radial velocity of the star changing is by looking at its spectrum. Right. So it's about time to start talking about spectrum. Before that, just one more example about these light curves. They also are very important to characterize some other objects, namely asteroids. Asteroids, they don't emit their own light. They reflect the light of the sun. They're also very irregular. They don't have to be spheres. They can be, you know, stones like this. And when you have that stone that is, you know, moving around the sun, sometimes getting illuminated more, sometimes getting illuminated less, changing its relative position with respect to Earth, changing its projected size on the sky, combination of all these effects will lead to the fact that your light, your brightness of your asteroid changes with time. And in the same way that we could characterize the properties of the closed binary systems by looking at their light curves, we can characterize albedo, composition, shape of the asteroids by analyzing their light curves. And that's also very, very interesting because it allows you to basically probe the shape of these objects without actually traveling there and looking at them directly. You are just deciphering there. So keep in mind that you are not seeing its shape. You're just seeing this. And then you are inferring from the shape of this, the shape of the asteroid, which is very interesting. Okay, good. But now what we're going to do is we're going to try to get some more information from our light. So what we did first is we looked at the position of the objects, then we looked at the brightness of the objects, but now we're going to look at the brightness of the objects at different wavelengths. And the most natural way to do that would be to put something called filters on your telescope. But I think you've heard that story multiple times about these, you know, filter systems and so on and so on. So I'm going to jump over that and I'm going to go straight to the spectroscopy also because we don't have too much time and I wanted to make the spectroscopy the most important thing. One thing to keep in mind is that we never really see complete light coming from some object to us. The main reason for that is that it's impossible to make one telescope that can observe at all the wavelengths. Like if you make an optical telescope, it will observe a bit in the UV and a bit in the infrared. But if you want to go, for example, to extreme UV, you already need to make your telescope out of different materials. If you want to go to millimeter range, then you cannot use conventional telescope anymore. You need to use basically radio telescope or the antenna and so on and so on. The thing is that, of course, by looking at all the light from, let's say, 100 nanometers to 1000 nanometers is very often same as just looking at the whole light of the object. A lot of stars, for example, emit mostly in the, you know, visible, near ultraviolet and near infrared, and that's it. So it would be nice to separate this in a little bit more, in wavelengths a little bit more. One way to do it is through filters, but as I said, we're going to jump into something else, and we're going to now talk about spectral lines, photons, spectra, and all these things. And here are some of the important figures there, and some of these people you're recognizing, maybe. This is Cecilia Penka-Poshkin, who explained the differences between the stellar spectra. This is Ann Cannon, who did one of the first classifications. These are Kirchhoff and Bunsen. So Kirchhoff, you know, from various, you know, problems in currents and so on, but Kirchhoff was actually the guy who first figured out that black body has to exist. So Kirchhoff was maybe one of the most important things for the starting of the development of spectroscopy, and Bunsen was his, you know, colleague who experimentally helped him measure some of these things at the beginning. This here is Carl Schwarzschild. You know of him probably from the Schwarzschild black holes and his, you know, theory of gravitation and so on. But he was actually one of the first guys to tackle something called radiative transfer. Radiative transfer is the theory that tells us how the radiation propagates through the atmospheres of the star and the sun. And he tried to explain why the spectra look the way they look. And this here, of course, is Albert Einstein, who postulated the existence of photons and who actually allowed us to really understand why the spectral lines exist and what is happening there. And this is Fraunhofer here, a guy who was one of the first people to see these famous Fraunhofer lines in the spectrum of the sun and to name them. So this here actually is one of the first I don't want to say recorded, but in a way recorded, because this guy tried to make very precise sketch of what he measured. And this is basically a solar spectrum, originally as it looks in the works of Fraunhofer from 1814. So more than 200 years ago, Fraunhofer took a telescope, or not even a telescope, maybe just a crack in the camera obscura, put that light through a prism, and then what did he do? He first looked at that light. He could see some distribution of the colors there, but because his experiment was a little bit more precise, he could actually see some dark lines in the solar spectrum. He saw that the light was missing in some of the wavelengths. All right. What he also did very cleverly, he used the thermometer to see how much of each color he has. So he would put a thermometer behind of each color and see how much the temperature rises, and then note that. And he was able to map that way the distribution of the light over the wavelengths. He was able to map the distribution of the light of the sun over the wavelengths. And you can already see that it looks like something that we know as a black body curve. It's not exactly a black body curve. If it really was, there would be no spectral lines. I will try to convince you of that in a little bit. But this is one of the most important results for the development of our understanding of the stellar spectra, but also for our understanding of quantum mechanics. Because the existence of these lines here is very important. It was very important for us to put in the context with the atomic models that were, popping up at the beginning of 20th century. Good. Well, basically, this is what Fraunhofer did. Fraunhofer was mostly an optician, so he wasn't too concerned with explaining the shapes and the positions of these lines, but the people who were these guys, Kirchhoff and Bunsen. And what Kirchhoff and Bunsen found out is that they found out that the spectrum of the sun looks very similar to the spectrum of a very dense gas that they could make in a lab and heat it up. Basically, the spectrum of such a gas would also be something called continuous spectrum. However, if they put a dilute gas in front of such a hot source, like for example the sun, what they would get is that in this spectrum that was previously continuous, they would see these dark lines here. And we call them today spectral lines. So basically light at some wavelengths was missing. Right. If they did that without background, what they would see is they would just see these lines here. So from absorption, these lines would become emission lines. So if you ever get really interested in spectroscopy and we meet again and we start talking about this, I will tell you there are no absorption lines and emission lines. There are only different boundary conditions. But we don't have time to explain that today, so maybe some other time. Okay, good. And this was very important thing. Everybody wanted to understand why is this happening? Why is the light from a specific gas, when I put specific gas here, why is the light missing at specific wavelengths? I change the gas, the spectral lines change. Right. You now know that this is because different elements have different electronic configurations, which mean they have the different distribution of the energy levels within them. So that these basically wavelengths here correspond to transition between these levels. Right. That's something that you're familiar with. Are you? I think you are, right? Probably you are most familiar with the basic, model of hydrogen where you have these energy levels which are like 1 over n squared, but every element has some, electronic configuration and some distribution of these levels, and then they typically have much more different configurations, and that results in much more different spectral lines. For example, iron has probably millions of spectral lines because it has very complicated electronic configuration. Some other metals also have a lot of spectral lines, and so on and so on. But these people didn't know that. They only could say, I put sodium here, I see these spectral lines, oh wow, there are these spectral lines in the sun. That must mean that sun has sodium. Then they do same for magnesium, they do same for chlorine, and so on and so on. And some of the spectral lines they couldn't identify. For example, helium, they could see its spectral lines in the sun, but they couldn't reproduce it on the Earth. And eventually, they figured out, oh, it's not some special element, it's actually this element helium that we also have on Earth, we just didn't know, etc., etc. Right, today, of course, we see these spectra in much more detail, and I'll spend some time telling you about the exact shapes of these spectral lines and what these shapes are telling us, but this is now one of the more precise versions of the solar spectrum. So this spectrum would be so long that we had to fold it, right? It starts from here, and then it goes, zigzag right here, all the way from red down to blue. And you see that these spectral lines, these places where the light is missing, that they are not just some simple blanks, some of them are stronger, some of them are weaker, and I really have a lot of them. And actually later I will plot them as a graph, and you will see that even this, what we see here, is a minor part of all the spectral lines that we can see in the spectrum of the sun or sun-like stars. Right. And people, they started very quickly observing the spectra of other stars, not only the sun, right? Of course, it's a little bit more demanding because other stars are much less, they have much smaller apparent brightness, but eventually they started looking at their spectra and they saw that the spectra of different stars looks different, but that they can group them in some, similar groups, and eventually they emerged with this very well-known classification, O, B, A, F, G, K, and M, and then we had some other spectral classes, and actually this here is one of the most interesting, plots for me. By the way, one of the most important contributors to this classification was Annie Jump Cannon, who was an astronomer from the first half of the 20th century. And here we have some example of some observed stellar spectra. So these are now all stars of different, what we call spectral classes, right? And their spectra looks different. So first of all is that the spectra has been normalized in such a way that we don't see that, for example, this star is brighter than this star here, or that there is more blue here than here, and so on. So the color distribution has been polished completely. But what we see is that the existence and the strength of the spectral lines is different. All right. So can somebody tell me now, first, what are the spectral classes consequence of? Why do we have different spectral classes? What is different between these stars? Temperature. Very good. So temperature, we first time when we learn about spectral classes is we learn about different temperatures, meaning different colors, right? Yeah. The more warm stars are blue, the more cold stars are red. But now I want to go in a little bit more complicated story here. Does anybody know which spectral line is this one here? It's a red spectral line. Wavelength around 650 nanometers. H alpha, exactly. H alpha is which spectral line? Which transition does it correspond to? From second to third level of neutral hydrogen, right? So this is n equals 1, ground level. This is n equals 2, this is n equals 3. And now, spectral lines are not only consequence of absorption processes. They are the consequence of a complicated interplay between the absorption and emission processes that happens in the atoms. All right. And I will, as you said, I will draw it like from second to third, which means I will draw it like the electron going from the lower level to the higher, which means that we have absorption. But I don't think we'll have time today. So sometimes, again, in the visual future, we can talk about what actually happens here. Cool. So H alpha exists. Now, keep in mind, this is very low resolution. H alpha is very strong line also in the sun. But when you plot it in such poor resolution, you barely see it. Where would sun be? Sun would be here, right? Somewhere here, right? So we very, well, maybe more close to G0, right? So we see it very, very faintly. On the screen, it's a little bit stronger, but here you barely see it. But for example, for A0 stars, you see that it's much, much stronger. Of course, this doesn't mean that A0 stars have more hydrogen than the Sun. All stars have mostly hydrogen. That's like what we know today for sure. But this was very confusing to people in, what was this, maybe 20s, like 100 years ago. They thought that the presence of these spectral lines has something to do with chemical composition. And then it was very confusing because that would mean that these very cold stars have much more metals and much more molecules. Well, molecules they do have more than these stars here. But that's not what happens. And the person who figured that out was also a woman, Cecilia Payne-Gaposchkin. And she actually explained that most of the stars have very, very similar chemical composition and that there's something else that is happening. Do you maybe know why is H alpha so strong in A0 spectral class, much weaker in J0 spectral class, and much weaker in O spectral class? Any ideas? Let's start from this thing here. So where does all this thing happen? In a neutral hydrogen, right? Let's call it H0. Right. So to get the absorption at this wavelength, the first thing that I need to have is I have to have neutral hydrogen, right? Why would I not have neutral hydrogen in O stars? Does anybody have an idea? They're very hot, and then what happens?
We can find only particles of hydrogen in the stars.
Once again? What the hydrogen gets ionized, right? Okay, so if the star is very hot, the temperatures of O stars are tens of thousands of Kelvin, right? It's very hot stars. At these temperatures, hydrogen is completely ionized. If the hydrogen is ionized, it means that it has no electrons, there are no transitions in there, there cannot be spectral lines, right? So we explained why in the very hot stars I don't see the spectral lines of hydrogen. But okay, these stars here are even colder, so hydrogen should surely be neutral, yet I don't see its spectral lines. Why? What is the other thing that I need to have? I need to have neutral hydrogen in which state? In this state, right? So I need H0 in n equals 2. What determines actually, let's first point out that this is not the ground state of hydrogen, right? Most of the hydrogen atoms are going to be in this state here, in the ground state, right? What determines how many of my atoms are going to be in the state n equals 2? Which physical quantity? Again, temperature, right? There is the distribution called Boltzmann distribution, which says that probability of finding my electron in some state n is proportional to something called statistical weight of this level n, which is something that you surely remember from the high school, which is this 2, 8, 18, blah, 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 and times much more important factor e to the minus en over kt, which means higher is the energy of the level, less probable I am to find my electron in that level, but higher is the temperature, because this exponent is smaller and it has minus here, larger is the probability that I will find my electron there. And this is a very steep function, right? And if you go from these like 5,700 Kelvin for the sun, up to like 10,000 Kelvin for the A0 stars, this number here for n equals 2 increases many times. And what I actually have is that in these stars, I will have much more hydrogen that is excited to n equals 2 than for the Sun, and I will have much stronger H alpha line. And now you can apply the same basically reasoning for everything. You can see that the same happens for H beta line, which originates from the same level. It just goes all the way up to 4. So it's basically the same story. But then you can also analyze the lines of metals. The lines of metals disappear very quickly because metals get ionized very quickly, and so on and so on. And Cecilia Payne-Gaposchkin figured this out, and she figured that out by plotting these two important probability distributions, one of which is this Boltzmann distribution that we wrote over there. The other one is so-called Saha distribution, which governs the distribution over the ionization stages. And she figured out that basically different spectral lines will be visible in the stars of different temperatures, even if those stars have completely same chemical composition. Of course, to really model this, to really understand what is happening, you can't just, hand wave and look the equations like I did. You actually have to put these things and calculate them. And that's a cumbersome process, and I will show you some results of these calculations soon. Right. As you all know, these spectral lines and their observation and measurement of their energies and so on was crucial for the development of atomic models and quantum mechanics and so on. And one of the simplest ways to explain this would be the Bohr's atomic model, which, as you know, only worked for hydrogen, right? It had these very simple, expressions here, where basically the energy of a level is proportional to 1 over n squared. Actually, the ionization energy from a level to the continuum is proportional to this, right? And in principle, people then try to, make imitations of this formula for other atoms, but then over time they developed quantum theory, so they were basically able to calculate these energy levels very precisely by solving Schrödinger equation for more complicated and more complicated systems. And they found that these energies, calculated were corresponding very precisely to the spectral lines. And basically the observations of the spectral lines, both in the lab, but also in the stars and the sun, allowed them to test quantum theory and to figure out what happened. But this is also a story for another time. But one more thing that happened, I won't force you to read this one now, even though, I hope we will do it, is how this all fit with what Einstein did, right? You all know who Einstein is. What you also probably know is that the discovery that he made, for which he was formally given the Nobel Prize, was the discovery of so-called photoelectric effect. Photoelectric effect is basically one of the first at least experimental confirmations that photons behave like particles. What was the problem? The problem was that if you take a piece of metal, in this case it's potassium, you illuminate it with red light, nothing happens. You illuminate it with green light, suddenly electrons start popping out of this metal, and you can measure their energies by putting that in some potential difference. You illuminate it with blue light, the electrons are still popping out, and now they have larger velocities. And this was completely unexplainable. You could not explain this by the classic theory of radiation. What is classic theory of radiation? It's the one that follows from Maxwell's equations, right? You could not explain this. So what you had to do to explain this is to invoke the assumption that light can behave as a particle. And if the light can behave as a particle, then, and its energy is proportional to the frequency, then for the higher frequency, you have higher energy, it behaves as a particle, it's able to knock out the electron, and you have photoelectric effect. If it doesn't have enough energy, it is not able to knock out an electron, we don't have the photoelectric effect. Why did I tell this? Well, I told this because this is not exactly, but practically it's the same mechanism as the spectral lines. If you have some energy gap and you find the photons of the exact that wavelength, you will have the spectral line. You will have that absorption over there. If you don't, there won't be any, right? And the spectral lines are basically a consequence of the fact that light can behave as a particle. Of course, you can derive the spectral line and spectral line transitions from classical theory and so on, but it simply is much more intuitive if you do it this way. And then we could finally understand Kirchhoff and Bunsen's results that, you know, when these lines here correspond to various gaps. I just put the hydrogen here for the illustration, but it of course can be some much more complicated, you know, energy levels and the transitions and so on, right? And the whole, I'm going to tell you again, we won't derive it right now, is that the whole difference between these two stories here is just the boundary condition. If I have the bright light in the background, what I actually have here is that there is simply a lot of light is absorbed, but not enough of light is emitted to make up for that absorbed light. So I see dark lanes, I see absorption. Here, what I see is I only have this, you know, tiny flame here, so I only see the emission processes, and then I see this light as bright. So this here, well, how I like to call it, it's not absorption, it's just not sufficient emission, right? And we know that because to really have pure absorption, you would have to have very cold gas. And we don't have cold gas in the stars. The spectral lines in stars are formed by their atmospheres. The atmosphere of the star is this part where the temperature, well, first of all, actually, we have a slide for that. Yeah. Just before that, let's just see what the stars actually are. We imagine them as huge gaseous spheres which have temperatures of millions of Kelvin in their cores, so they can create energy there through fusion, right? And then as we go outward, the temperature is falling down. Why is the temperature falling down? Because the energy is being propagated outwards, right? If you want to propagate energy outwards, you need to have negative gradient of the temperature going outside, right? Simply the energy goes from the hotter to the colder part. And the first approximation of what we see when we look at the star is that we see some black body. You probably all heard about black bodies before. We're not going to go there, but if you don't understand anything, interrupt, of course. If you don't understand something, just interrupt and ask me. And the simplest way to express what would be the energy emitted by the star in the unit time is what we call luminosity, is the surface of the star times some constant, which is called Stefan-Boltzmann constant, and times some temperature to the 4. Now, the good question is, what is this temperature? How do we call this temperature that enters this equation? Effective temperature, right. The thing is that if I tell you effective temperature of my star is 5,777 Kelvin, that doesn't tell you so much. That's basically just different way of me telling you this number L, or this part sigma t to the 4. Why? Because the stars don't have one temperature. The temperature is a function of R, or of height, if you want. And actually, what happens there, sorry for this, I don't see my following slides. I'm just going to jump here for the moment, and then I'll go back. What we actually have is that there is a distribution of temperatures in the atmosphere of sun and stars. And what we actually see when we look at the spectrum is different contributions of different layers at different wavelengths. So what we mostly see is we see this layer called photosphere, for which we can say, okay, the light that comes here comes from the temperature of around 6,000 Kelvin for the sun. But when we look at the spectral lines, the light that is what we call absorbed, is actually coming from the higher layers, which are colder, which are both absorbing and emitting, but they are simply not emitting enough to compensate for that absorbed loss, so we see them as absorption lines. If somehow magically the temperature in the sun was increasing outwards, we would see these lines as emission lines. And that actually happens because the atmosphere of the sun is very complicated, and it goes and cools down, the temperature drops down, it reaches something called the temperature minimum, which is around 4,400 Kelvin, but then it starts rising. And it rises first to like 10-ish thousands of Kelvin, what we call chromosphere, then it plateaus, and then it jumps to millions of Kelvin, and then we have corona that is very, very hot. And this just tells you that simple diffusion of the energy outwards is not only mechanism for transport of the energy in stars, otherwise we would have continuously decreasing temperature. And one of the big open problems in the physics of the sun and consequently the stars is that we don't understand why these temperatures are so high. We don't know which mechanisms transport this energy there. It could be waves, it could be some sorts of small explosions, it could be various other things, but we never really measure them. Yeah, one thing to note is that this layer here, this stellar atmosphere, is it's looking by mass, it's completely unimportant compared to the rest of the star. The majority of the stellar mass is in its core and in the envelope. But the stellar atmosphere is the only part that we can see. And this was actually the discussion between two very famous astrophysicists. One was Edward Salpeter, who was one of the most famous stellar physicists ever, who asked Dmitry Michalas, and Dmitry Michalas was maybe the greatest expert ever for spectroscopy and radiative transfer and so on. How come that these atmospheres are so important since they are so small and insignificant? And the answer for that is because that's the only part of the star that we can see, right? I look at the star, I see its surface layers. From these surface layers, I have to decipher everything else, the structure of the star. By looking at, for example, the changes of spectral lines, I can decipher how the inner distribution looks like through helioseismology or astroseismology and the things like that. It's very, very important to understand that because that's the only layer that we can see. And sun there plays a very special part. Why does the sun play a very special part? Because it's the only star, well, almost only star, that we can see resolved. What does it mean resolved? Well, most of the stars, when we look at them, they're points. They're so far away that we don't have such a big telescope that can resolve these stars. So here is a little exercise. If you had telescope 10 meters big, looking at optical wavelengths, your angular resolution would be this, 0.012 arc seconds. Okay? If you took sun and put it just 1 parsec away, it would be this big. 0.004. It would be smaller than your spatial resolution, which means you would literally see it as just a dot. You couldn't see any details there. The only stars today that we can see any details, that we can resolve with any details, is the stars that are so big, that are basically some supergiants, something like that, that are simply physically so big that we see some detail there, or the stars that are so big and so close that we can look at them using so-called interferometric methods, so we see some detail on the stellar surface. But none of these are stars in any way similar to our sun. So for stars similar to our sun, we cannot resolve any detail there. However, here is image of one of the best telescopes, one of the best solar telescopes today. This is so-called Swedish Solar Tower. It's at La Palma in Canary Islands. And it has a diameter of a little bit more than 1 meter. And the actual resolution there, so obviously you see that it's not exactly 10 meters and 1 meter. This is a little more than 1 meter. The resolution there is 0.083 arc seconds, which corresponds to 61 kilometers on the surface of the sun. And the radius of the sun is 600,000 kilometers, which means that if I made each of my pixels this big, I could make a photo of the sun which is 20K times 20K pixels. For, what is that? 400 megapixels. That would be very hard to do because typically with telescopes like this, we look at the small pieces of the sun, but we see such small details. And recently in US, they made even bigger telescope, 4 meter wide, dickest. And with that telescope, you can resolve details down to 20 kilometers. And this is one of the best images of the solar surface that we can make today. This is how sun looks when you zoom a lot into it. And the physics behind this is relatively well understood. We know that these bright parts here are what we call granules. This is very similar to bubbling of the earth when you're cooking, when you're making tea or something like that. The warm parts are coming on the top, the cold parts are falling down, right? But we also see some other things. This is what we call filigree, or sometimes we call it bright points, which are these bright parts in between the granules, which are almost surely consequence of the magnetic field. So in these parts, we have a small magnetic field, we call them tubes, that are sprouting out of the solar surface, and they are changing the structure of the atmosphere in these points, and because of that, they look brighter than what regular intergranular lane would look like. We have a video to accompany that, where we can see a little bit how all that thing is changing. This here is because of my computer, it's not because of the video. To make these photos, they had to have 4-meter telescope with really good observing conditions. That's why they put it on Hawaii, on a very tall mountain where everything is very stable, surrounded by the ocean to stabilize the atmosphere. They used something called adaptive optics. Adaptive optics is a technique where you have, after your mirror, after your primary mirror, you have a deformable mirror that tries to undo that effect of the atmosphere that I was telling before, to basically straighten again your wavefronts, to make your picture nice and sharp again. And then finally, they use these post-processing techniques where you try to infer the shape of your PSF and additionally deconvolve your image. Right. And just to show you one more thing, the spectral lines are much more complicated than what we would think, right? So here you see these two orange spectral lines of sodium, right? And for you, these are just two dark blips. When we zoom in them, we see that these spectral lines, first of all, they have some complicated shape. They are not just rectangles that I cut out from the spectrum. They have some complicated shape. They're very deep. They are almost reaching zero. But there are more very, very weak spectral lines in between that we couldn't even see in that other view. And actually, by analyzing the shapes of these spectral lines, why are they so wide? Why are they so deep? Why are they wider here and more shallow here and more narrow here and blah, 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 blah? We learn a lot about the vertical stratification of the atmosphere of sun and stars. We learn how the pressure is distributed with height, how the temperature is distributed with height. We can even infer the presence of motions that we cannot see because we don't resolve the star, but we can still infer that, there have to be some, we call them turbulent motions in the atmospheres, and so on and so on. So, and of course, we can infer the exact chemical composition of these objects because we can calculate this, we can perform very complicated calculations and compare them with what we see and see how much, for example, of sodium I have to have there to reproduce this or any other species or something like that. So this is why by using spectroscopy, and there are of course many more examples both in galactic astrophysics, intergalactic astrophysics. Thanks to spectroscopy, we can, we confirm the existence of intergalactic gas and so-called and so on and so on. So there are many, many other applications, and really spectroscopy and spectropolarimetry, which is then measuring polarization on top of all this, which we won't be talking about now because we are literally finishing. This is why this spectroscopy and all these techniques really allowed us to understand the physics of these objects. So not only how they attract each other, how they move, but what is happening on the inside. And that is why people typically say that what Kirchhoff and Bunsen, these first guys who observed the spectra and connected them with the physical properties, that is why they gave birth to what we call now astrophysics. So now typically when you say I'm doing astronomy, everybody implies that that means astrophysics because most of the research today we would typically call astrophysics. Okay, good. This is the end. Thank you for the attention and for